Okay, this is MEN 415 HeFlow Lab. Today we are going to talk about lab number 6. Okay, so this is a classic conduction convection heat transfer problem. Okay, so we are going to use an apparatus to verify the conduction and the convection. Okay, so let me share my screen here. Let me turn to our handout, Lab 6. Okay, here it is. Okay, so this is the handout I posted on Moodle. Okay, so let me show you the apparatus first. Okay, so this is the Pascal heat conduction apparatus. Okay, this is the apparatus, and it is connected to the power supply. So there's an electrical heater in the center. Okay, connected to the power supply here. Yeah, we use 5 voltage. So we'll heat it in the center. So the heat will be transferred to the 4 metal bars here. Okay, if you can see, if I can enlarge it a little bit, see that there are 4 metal bars. The top 2 bars are brass. The bottom left is aluminum. The bottom right is stainless steel. So 3 different materials. For the 2 brass bars, one is bigger, one is smaller. Okay, you have bigger cross sections. The other one has smaller cross section. So we can also see the heat transfer effect based on the cross-sectional area. Okay, so center will be heated. Okay, the heat will be transferred to the 4 bars. So we can measure the temperature, the temperatures on those A locations. Okay, 2 points for each metal bars. 1, 2, 3, 4, 5, 6, and 7, 8. Okay, so temperature difference between the 2 measurement locations, you can use that temperature difference to calculate dTdx, right? Temperature gradient times K times the cross-sectional area. That will be your conduction heat transfer. I think I listed in equation 2. This is the conduction heat transfer equation, Ka dt or dt over dx. It should be derivative, right? But in the experiment, what we do is we use data. We measure the temperature difference. We measure the distance between the 2 points, okay? So on each bar, you should be able to calculate a Q, conduction heat transfer. By the way, this is the 1D conduction. So basically when you do experiment, there will be a insulator cover. It's a cover all 4 bars. So there should be minimum heat transfer through the side of the metal bars. So because it's insulated to the side. So the 4 ends opens to the atmosphere. So there will be heat transfer going out through convection. But inside the material will be conduction, and it's 1D because the side is covered. Okay, it's insulated. Okay, so in each bar, you should be able to calculate a Q. Okay, heat transfer, conduction heat transfer rate. Now you know, you already did the previous heat transfer cross-flow heat exchanger experiment. You know the electrical heat generated should be equivalent to the heat transfer through the 4 metal bars, right? So there should be a heat balance, okay? Since you connected this thing to the electrical heater, okay? So you know the voltage, you know the current, okay? So based on this, you should be able to calculate the power, right? Voltage times current is the power. The power watt should be equal to the total heat transfer through the 4 bars. So Q1 plus Q2 plus Q3 plus Q4, supposedly it should equals to the total heat generated in the center. Okay, so that's the first thing I want you to verify, the heat balance. Okay, well, I think you can tell the total heat generated will be lost a little bit. Okay, from the heater, and we'll have a little bit loss, and also they're a little bit lost to the side. Okay, the insulator is not perfect, so the summation of the 4 Qs should be smaller than the total heat generated. That's reasonable. Okay, it shouldn't be bigger. If it's bigger, then that some problem with your measurement. Okay. So that's one thing I want you to verify, to see total heat generated in the electrical heater. Does it equals to the conduction heat transfer in 4 bars? Okay, the summation of the conduction heat transfer in the 4 bars. Okay, so that's the first task, I think, for this lab. Okay, the second task is this. Okay, so we know in our heat transfer class, I think it's in chapter 2, right? We talk about this. So if you have a conduction go through the end of the bar, and there will be convection to the surrounding QH. Let's say this is a Q conduction, QC. How about that? Conduction, convection. Let's say QH is a convection. Okay. So what's the relation between the conduction and the convection? Do you by chance know? Still remember? You should, right? We did the previous cross-flow heat exchanger experiment. You know, actually, that should be equal. Q conduction should be equals to the Q convection. Okay, convection. Okay, so now look at the handout. The equation 3 is the convection equation. So convection equals to conduction. You can already measure. I think I give all the conductivities for the different materials. You measure the cross-sectional area, and the dx, right? The delta t, delta x, delta t is just the temperature difference between the 2 measurement points. The distance is 3 centimeters. Notice it's not 1 inch. It's a little bit greater than 1 inch. Okay, so that's the distance between the 2 measurement points. And also it's 3 centimeters from the second measurement point to the end of the bar. It's also 3 centimeters. Okay, so that's the dimension. The cross-sectional area, I give you the data. Okay, so based on equation 3, the conduction you already measured. You have the value. Okay. Convection is HA delta T, which is the T at the end, let's say T surface area, at the end of the bar, minus T infinite. Okay, T infinite is room temperature. I think it's also on the data sheet. Okay, it's about 75 degrees. Okay, so this is delta T, T surface end of the bar, minus T infinite. T infinite is the room temperature it's given. So area is given. Okay, the goal of this lab, the second part of the lab, is to find out what's the convection heat transfer coefficient of the air in adjacent to the metal bars. Okay, so we know the conduction equals convection. Conduction value we know, okay? Area we know, delta T. So we need to know the delta T in order to calculate the H, right? One equation can only calculate one unknown. So we need to know the delta T. We know T infinite, but what is the surface area, surface temperature, Ts? Okay, so in conduction, you know the temperature change linearly. You know the equation, first order derivative, right? Conduction equation here, equation 2. dt over dx. So it's first order derivative, k times a, okay, constants. So it should change linearly inside this bar. So you have the temperature of the 2 points. do a linear interpolation, you should be able to find the temperature at the end of the bar, which is TS. Okay, linear interpolation. So I think you know how to do linear interpolation, right? So TS should be obtained easily because the distance also 3 centimeters between the second measurement point to the end of the surface. Okay, also 3 centimeters. Between the two measurement points is 3 centimeters. So you know the two temperatures, then you should be able to figure out the ending temperature TS. Okay, so then with the TS, you should be able to find out what is the H in adjacent to your bar. Okay, so you have 4 bars. So you should be able to calculate 4 H's. The 4 H's should be similar, but it's not exactly the same, okay? So if you want to determine the convection heat transfer coefficient of the air in adjacent to this device, you can just simply average them out. Average all 4 H's you determined. That's your convection heat transfer coefficient of the air in this experiment. Okay, that's the second task of this experiment, okay, to find out the H adjacent to this device. So after you find it H out, I want you to verify the H to the literature data. You have a lot of online resources to tell you what is the convection heat transfer coefficient and a certain temperature, okay, under different wind speed. Okay, so that wind speed here is pretty low. Okay, you can assume it's a still air in the experiment. Although in the room you have some AC flow, but it should be minimum. Okay, so find a literature H value for air under that room temperature, under the still air. Okay, compare your measured H to the literature H to see how close they are. Okay, so that's the 2 tasks for the experiment. Okay. Let me also show you some other pictures of the experiment. Okay, when we do this experiment, okay, we connected one end of the device into the power supply. I already showed you. The other end, this port will be connected to the temperature array, which will be connected to a computer. Actually, there's a software, Data Studio, installed in the room, in the ETL 109, right? And every computer can read the temperature data. I show a screenshot here. You see 1, 2, 3, 4, 5, 6, 7. There's 8 temperatures, okay, for the A measurement point. Okay, so 2 temperatures for each material. It can be directly shown on the computer. So the measurement is easy. But when you do this measurement, it is a transient process. When you start heating it, it won't heat immediately. It takes time to reach to equilibrium. And actually, when you do the experiment, you need to sit there for about 20 minutes for the temperature gradually reach to equilibrium. Okay, temperature become stable. Okay, so then we record the A temperature values. Okay, so based on the A temperature values, you should be able to calculate these values required in the report. Okay. Let me show you the data. I think I have a data sheet. Okay, let me open it. Show you what the data sheet look like. Okay. Let me share my screen. Okay, so this is the data sheet. The first table shows the powers, actually the voltage and the current, okay, voltage and the amp. Then it calculated for you. This is the power, total power input into the center of the unit, okay, heater, electrical heater. So for the 4 bars, thick and thin, it gives you all the width and the height. So this is the cross-sectional area. Okay, it calculated for you. And this is thermal conductivity, K. Okay, so notice the stainless steel has a very bad heat transfer, only 14 comparing to the 100s for the other three materials. Then these are the temperatures. Okay, room temperatures in Celsius. Okay, room temperature doesn't change much during the for the actually for each of the bar, each of the measurement location, we can actually measure room temperature without turning on the heater. So the temperature on the bar is basically room temperature. So we actually measure the room temperature, but they are similar, about 18 degrees Celsius. Okay, so this is the temperature on the A locations, 1, 2, 3, 4, 5, 6, 7, 8. Okay, so this is the data that you needed for the calculation for this lab. Okay, so this is lab number 6. Okay, I will post the handouts and the data, and I will also post this video. Okay, so it will be due in 1 week.